Okay, take 2 of lecture 2.6. I can see that my talk button is working and I am being recorded. So we can get this time. I have confidence in myself. Here we go, lecture 2.6. So the first thing that you encounter in lecture 2.6 is the definition of a rational function. And a rational function is just a ratio or a division, either or, you can say it either way, of polynomial functions, meaning that I'll have an expression in the numerator and an expression in the denominator, and that expression in the denominator will have a variable in it. Doesn't always have to have one in the numerator, but if there is a variable in the denominator, then it is a rational function. Now notice q of x, which is the function in the denominator, cannot be 0. Because if that function is 0, then the entire function is undefined because you can't divide by 0. So this leads us to the topic of the domain of a rational function. The domain of a rational function is the set of all real numbers except the x values that make the denominator 0. So we have to throw out anything that if we were to plug it in would make the denominator 0. So how do you find the domain of a rational function? Well, you focus on the denominator. You take the denominator and you set it equal to 0. And if you solve that equation, that will tell you all of the x values that could make that thing 0 there. Well, lucky for us, this particular one is already factored, so all I have to do to solve is apply the zero product property. So I get x is 0, x minus 2 is 0, and x plus 5 is 0. So x is 2, x is negative 5. These are not good. These are the ones you don't want to have in your domain because it will make the denominator 0. When you state the domain, you state it in interval notation, and you are stating what x can be, not what x can't be. So x can be anything from negative infinity to negative 5, or negative 5 to 0, or 0 to 2, or 2 to positive infinity. Okay, notice all of these are parentheses, meaning up to but not including. So we're skipping over negative 5, 0, and 2, writing it that way. If you're not fresh on your interval notation, you'll want to go back and, goodness, I can't remember which lesson that was, but there's a whole section on interval notation where I introduce it and talk about all the ins and outs of it. I know it's in chapter 1 somewhere. All right, let's move forward. So write the domain of each rational function. So I just need to focus on the denominator. Here, x minus 5 equals 0, meaning when x is 5, that entire denominator is 0, so x cannot be 5. My domain is anything from negative infinity up to 5, non-inclusive, and 5 to positive infinity. Now when I look at this next one, I have x squared minus 25 equals 0. X squared minus 25 is a difference of squares, so I could factor it and use the zero product property. X plus 5, x minus 5. I could have also used the square root property to solve that, but I'll show you that in the next one. So here x plus 5 is equal to 0, x minus 5 is equal to 0, so x is negative 5, x is 5. These two values are excluded from the domain, so the domain is negative infinity to negative 5, then from negative 5 to 5, and then from 5 to positive infinity. Now this last one, x squared plus 25. Okay, so this is not a difference of squares. This does not factor as x plus 5 times x minus 5. This is the difference of squares. Notice the difference, the subtraction sign. This is a sum of squares, and there's no way to factor this thing. This thing's actually prime. So if I start using the square root property to solve for x, take the square root of both sides, I get x is equal to positive or negative 5i, because I'm taking the square root of a negative number. These are imaginary numbers. Notice in our definition of a rational number, a rational function, the domain is the real numbers. So what this says is the only values that I would exclude from the domain are imaginary, and nobody's going to plug in imaginary numbers anyway. So my domain is negative infinity to positive infinity, because I can plug in any real number I want to. The only restrictions there are imaginary numbers. Okay, moving along. Okay, so one of the very first rational functions that we get to is the reciprocal function 1 over x. This is a parent function. I have done no transformations to it. So let's talk about the domain first. Basically, the only thing we can't plug in is 0. So my domain is from negative infinity to 0, and from 0 to positive infinity, non-inclusive there on the 0. When you have no idea what a function looks like, a good place to start is an f of x table, so you can start to get an idea of how this thing builds onto the graph. All right, so when I plug in negative 10 for x, here I get negative 1/10, negative 1/5, negative 1. I actually get negative 2 here, and I get negative 10. All right, and I'll fill in the positive values here. So this is positive 10, positive 2, positive 1, positive 1/5, and positive 1/10. Now I'm going to go and put these on the graph. Negative 10 1/10 is barely off of the x-axis there, so I've got it touching it. It's not on it, but it's touching it. And then the point negative 5, 1/5 is a little bit higher, but not much. Still a very small number. Negative 1, negative, oh, I'm in the positives. Let me flip-flop this to the other side of the graph. Sorry about that. You know, I think I did the same exact thing when I recorded this lecture last night without recording myself talking. Okay. 1, 2, 3, 4, 5, negative 1/5 is about right there. Negative 1, negative 1. Negative 1/2, negative 2. Negative 1/10, negative 10. It's all the way down here. Okay, so this piece goes like, if I can hit my marks, goes like this. Yeah. I've not fed the dogs. I didn't have time. All right, and graphing the other side of that, 1/10, 10 is about right here. 1/2, 2. 1, 1. 5, 1/5. And 10, 1/10. So this piece goes this way. And we'll come back and look at this graph even more in a little bit when we start talking about asymptotes. So notice this is centered around the origin, and so it has origin symmetry, and we'll move forward. All right, arrow notation. So arrow notation is used throughout our discussion of rational functions. this is the notation that we have here. And what this says is, this first one right here says, as I'm moving through the x's, approaching some x value, and they call it a, from the positive side. So x approaches some value a from the positive side. Let's go back to our graph here. Let me get a different color. Okay, so I could be asked the question, as x approaches 0 from the positive side, comma, f of x approaches what? So I'm leaving a blank there to fill in. All right, so let me talk to you about what this is asking us. In my x values, as I approach 0 from the positive side, the question is, what's happening to my y values? Well, my y values, when they come towards 0 from the positive side, are shooting straight up. So f of x is moving into positive infinity there. As x approaches 0 from the negative side, f of x does what? So as x approaches 0 from the negative side, that's what the little superscript with the negative sign in it means, my function, my f of x, is approaching negative infinity. You can see it just drops right off the graph there. So that is what arrow notation is, and it's just a way of talking about the movement of the functions. So as x approaches infinity, we'll go back and get as x approaches infinity and as x approaches negative infinity. I'll change colors for these. So as x approaches positive infinity, so as x approaches infinity, f of x approaches what? Well, you can see in my purple that my purple graph is getting closer and closer and closer to the x-axis, which is a y value of 0, but it never gets there. So f of x approaches 0. As x approaches negative infinity, so this is my x values going to the left, my f of x is also approaching 0. So we could even be more specific and say, as x approaches positive infinity, f of x approaches 0 from the positive side. And as f of x approaches negative infinity, x approaches negative, f of x approaches 0 from the negative side. It's coming up from underneath there. So hopefully that clears up arrow notation for you. And we have another basic rational function to look at, and that is the reciprocal square function. So let's talk about the domain first. We want to know, when is x squared, or that denominator, going to equal 0? Take the square root of both sides, and we get x equals 0. So that's my only restriction for the parent function. So my domain is from negative infinity to 0, and from 0 to positive infinity. Okay, I'm just going to fill in these values real quick so you can see where that picture of that graph comes from. Okay, so when I plug in negative 5 squared, I get positive 1/25, because when I square negative 5, I get positive 25. So when I plug in negative 2, I get positive 1/4. Here I get positive 1. When I square negative 0.5, which is negative 1/2, I get positive 1/4, and then I do the division and come out with positive 4. And when I square negative 1/10, I get positive 1/100th. I do the division and get 100. Okay, I'm going to fill in my positive values, and they're no different because they're getting squared as well, and when you square that negative, it turns to a positive. Same thing here. The positive is going to stay. Same value when it gets squared. So 1/10 is 100th, 1/2 is 4, 1 is 1, 2 is 1/4, 5 is 1/25th, and I'll show you where these points are. So starting here, -5, positive 1/25th, right there. -2, positive 1/4, -1, -1/2, positive 4, and then the other one's off the graph. Okay, doing the positive values, 1/10, 100 off the graph, 1/2, 4, it's right there, 1/1, 2 1/4, 5 1/25th. And this is a screenshot from your book, so you can take time and go back and look at it, and it gives all of the arrow notations that you can talk about with this particular graph there. Okay, vertical asymptotes of rational functions. So, an asymptote. An asymptote is an invisible line that a function approaches, but it never actually reaches it. So it's the idea of a limit. And when we were just talking about the domain of a function, there were values that you couldn't plug in because it would make the function undefined. At those values, you will have one of two things. You will either have a vertical asymptote, or you will have a hole in your function. And we'll talk about holes in a minute. We'll focus on the vertical asymptotes first. So, locating your vertical asymptotes. If your rational function have no common factors in the numerator and the denominator, then those values that you found for x that were exclusions from the domain comprise vertical asymptotes. Okay, so let's take a look at some examples to help us better understand this. All right. So with this first example here, I'm trying to figure out where the vertical asymptotes live. Well, I do that same thing I did with the domain. I take the function in the denominator and see when it's going to equal 0, because that's where my function does not exist. And remember, at those vertical asymptotes, I'm never going to touch them. There's going to be no function at those vertical asymptotes. So this is where I start. So I have x plus 3 times x minus 3, because that's a difference of squares. So x plus 3 equals 0, x minus 3 equals 0, x equals -3, x equals +3. So notice I have a vertical asymptote at -3 and +3. Okay, so remember in the definition it said you're only going to have vertical asymptotes if that factor that you come up with does not divide out of the numerator. That's where the holes are. Vertical asymptotes have to be non-common factors in the denominator. So look at B here. We still have x squared minus 9 in the denominator, so that's x plus 3, x minus 3. However, notice we've got an entire factor of x plus 3 in the numerator. So I could divide that x plus 3 out That is where a hole is. And like I said, we'll talk about those in a minute. That is not a vertical asymptote at x plus 3. So that when we have x plus 3 equals 0, that's x is negative 3. There's no vertical asymptote there. Notice there's a hole. So if the factor can divide out, that is a hole in the graph. If the factor cannot divide out, so x minus 3 equals 0, x is 3, that is where you have a vertical asymptote. So hopefully now you understand the difference in finding holes and finding vertical asymptotes. Let's look at this last one. So I have x squared plus 9 equals 0, not a difference of squares, so I'm going to use the square root property. X equals positive negative 3i when I take the square root of both sides. These are imaginary values. We don't care about those. We're not going to plug them in anyway. This means you have no vertical asymptotes, because the only thing that's undefined there where the function does not live is in the realm of the imaginary. So notice in that picture there are no vertical asymptotes. Now there may be a horizontal asymptote, which we'll get to in a minute, but no vertical asymptotes. So holes instead of asymptotes, the value or the denominator for it does not necessarily result in the vertical asymptote. This is a hole, literally, corresponding to x equals a, and it's where the factor cannot be divided out. I'm sorry, where it can be divided out with the numerator. Okay. Horizontal asymptote. So, oh, by the way, let's go back to that very first graph we did. Notice the only thing that is not allowed in my domain is 0. It doesn't divide out that factor, and we have a vertical asymptote at x equals 0, which is the y-axis. We also have a horizontal asymptote, or that thing's approaching, but it doesn't touch. So let's go back and learn about horizontal asymptotes. Okay. So it's always going to be a horizontal line, y equals some value that the function will approach. The graph of a rational function may have several vertical asymptotes. We saw some examples of ones that have more than one vertical asymptote. By contrast, a horizontal asymptote, it can only have at most, oops, let me get off the yellow pen, at most one horizontal asymptote. Although, and this is important, although the graph can never intersect a vertical asymptote, it may cross a horizontal asymptote on one side. So here, not crossing, crossing on one side, but approaching on the other. So you can cross on one side with a horizontal asymptote. Okay, so I'm going to explain to you how to find where they live, and then it'll make a lot more sense when we look at the examples on the next page. So we have our definition of a rational function there, and the degree of the numerator is given by n. The degree of the denominator is m. So if n is less than m, then your horizontal asymptote is the x-axis, which is y equals 0. If n is equal to m, then you have to do the division of the leading coefficient. So notice the leading coefficient of the numerator is a sub n. The leading coefficient of the denominator is b sub m. So it's that line y equals the ratio of the leading coefficient of the numerator to the leading coefficient of the denominator. If n is greater than m, there is no horizontal asymptote. Okay, so let's make this clear as mud and look at some examples. By the way, there is a typo in the notes right here. This should not have a square on it. In that first example, it should just be X. Notice it's right here, but it's almost the same exact thing as this one, and I think that's why I have the typo in it from a long time ago. All right, so in this first case, the degree of the numerator is 1, the degree of the denominator is 2. So the degree of the numerator is less than the degree of the denominator, and that means our horizontal asymptote is the line y equals 0, which is the x-axis. So you can see if we extended this function, since we know that's an asymptote, it would go right up to it but not cross it. Same thing on the opposite side. Go right up to it but not cross it. Okay, so for example B, the degree of the numerator is 2 and the degree of the denominator is 2, so they equal each other, meaning we have to do that division of the coefficients, the leading coefficient. So the horizontal asymptote lies at the line y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator, which divides out to be 2. So notice we have a horizontal asymptote at 2 for that particular function. Now, with this last one, the numerator has a degree of 3, the denominator has a degree of 2. The numerator is greater than the denominator. That means no horizontal asymptote. Notice there's no horizontal asymptote in that graph. Okay? And I've got one page, I boogied through it. We're going to graph this particular rational function using these steps. These steps are a little bit different than the ones given in your book. However, if you want to use the ones from your book, go watch the quiz review, because I took you through all of the steps that your book has. I'm just taking you through the necessary steps here. The book gives a little overkill, in my opinion, but that's okay. All right, so the first thing we'll find are the vertical asymptotes. That is where the function is undefined and when that factor cannot divide out of the numerator, and it can't. So for the first one, we have x minus 1 equals 0. So we cannot have 1 in our domain, and it does not divide out, so that means we have a vertical asymptote at x equals 1. I'll go ahead and draw it on the graph for us. And I'm going to change colors with each step so we can keep up visually with what we're doing. So I'm doing number 1 in purple or violet. I'll do number 2 in green, horizontal asymptote. So I have to look at the degree of the numerator and the denominator. They are the same. So the line y equals the leading coefficient of the numerator over the leading coefficient of the denominator is our horizontal asymptote, and it is 2. So we have a horizontal asymptote. Let me make this line a little thicker, and I'll go back and thicken up that other one too so it can be seen a little bit better. Okay, there's our vertical asymptote. Okay, so those lines don't actually exist, but we put them there just to see our barriers with our function. Okay, so x-intercepts. I'll do x-intercepts in blue. And x-intercepts are what you get when you plug in 0 for y, so 0 for f of x. So 0 equals 2x minus 1 over x minus 1. To get that x minus 1 out of the denominator, I need to multiply both sides by x minus 1. So that divides out, and 0 times anything is just 0, so I get 0 equals 2x minus 1, add 1 to both sides, divide by 2. So I get an x-intercept, one of them, at 1/2. So I'm going to go ahead and plot that right between 0 and 1 on the x-axis, my x-intercepts, or my zeros, same thing. Okay, I'll do y-intercept in orange. So my y-intercept is what I get when I plug in 0 for x. So I just do f of 0 for my y-intercept. 2 times 0 minus 1 over 0 minus 1 is -1 over -1, which is +1. So my y-intercept is +1. Now, the last step is to just choose a few other points to find. I like to do about 3 on either side of any asymptote I have. So I'll do this last step in turquoise. And so I've already got 2 points, and I've got my asymptotes to kind of guide me. I've got 2 points to the negative side of my vertical asymptote, so I'm just going to find one more. I'm going to see what I get when I plug in -1 for x. So I'm going to do f of -1, which is 2 times -1 minus 1 over -1 minus 1. So that's -2 minus 1 over -2. So that is -3 over -2, which is +1 and 1/2. So when I plug in -1, I get out 1 and 1/2, which is about right here, like halfway between 1 and 2 in the y direction. So I can actually go ahead and graph that part of the function, that half. I'm going to make my stroke a little smaller. And so I know that it approaches those asymptotes but never actually crosses. So it's going to hit those 3 points and then fall straight down into -infinity. Okay, so I need to find some points on the positive side of my vertical asymptote. So I'll go back to my turquoise. And let's see, I've got on the positive side of my vertical asymptote, I've got, I could do 1.5, 2, and 2.5 if I want to. So I'll do 1.5, which is 1.5. 2 times 1.5 minus 1 over 1.5 minus 1. So that's 3 minus 1 over 0.5, which is 2 divided by 1/2. And there are 4 halves in 2. So I have the point 1 and 1/2, 4, which lives right here. 1 and 1/2, 1, 2, 3, 4, about right here. Okay. Now I'll do f of 2. So 2 times 2 minus 1 over 2 minus 1 is 4 minus 1 over 1, which is 3. So I have the point 2, 3 right here. And finally, I'll do 2.5. So 2 times 2.5 minus 1 over 2.5 minus 1. So this is 5 minus 1, or 4, over 1.5. And when I divide 4 by 1.5, I get about 2.67. It's a little more than 2.5. So I plug in 2.5, 1, 2.5, and I have about 2.5. So it's about right here in the center of that block. So you can see the trend. Let me get my orange again to draw this graph. Going to follow that horizontal asymptote but not cross it, and then it's going to, I'm sorry, the vertical asymptote, and then it's going to follow the horizontal asymptote but never cross it. Just get closer and closer and closer. And that is how you graph a rational function. So don't forget, Unit 5 quiz will be due this coming Monday at 11:59 p.m. It will open this Thursday at 12 a.m. The next lecture was today at 3 because I had to come back and re-record this one so that you could hear it. Don't forget that early bird registration is already open. For those of you that had that early bird advising appointment, if you didn't, registration opens for everybody else next Monday. So make sure you get registered for those fall classes. Good luck on your quiz. Let me know if y'all have any questions.